Right, so welcome to the first video of the differentiation video series. In this series, we're going to be looking at just the basic differentiation, looking at when we find stationary points, tangents, normals, and also looking at finding the maximum minimum values. So first things first, we're going to be looking at differentiating with first principles or from first principles. So what we know is if I was to draw a graph like this, what differentiating is dy by dx. This is how we write differentiation. Or sometimes it might be seen as f prime of x, okay? This just means differentiated or differentiation. And so what differentiation actually is actually finding the gradient of a certain graph or of a certain function. And so from the very basics, if I have maybe x here, and I'm going to increase by h, so x plus h, and then this part here, this y value will be f of x, and this y value will be f of x plus h if this was the function f of x, right? So what we know is when we find the gradient, our gradient we find is the change of y over change of x, right? So using this example, the change of y will be this value here. So it will be f of x plus h minus f of x. And change of x will be this term here, so x plus h minus x, which will reduce to f of x plus h minus f of x over h like this. So that's how we normally find the gradient. But with differentiation, when we find the gradient, it finds the gradient at one specific point, one point only. This here, what we've got here is the gradient over a large range, right? So what we can do instead is, well, I can say that dy by dx is actually finding limits as h tends to 0, meaning what happens when this gap h gets smaller, 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 ideally to 0 to a single point. And what we just deduced or proven is differentiation from first principle. And with this here, we can differentiate any function f of x. So let's say we have a function y or f of x is equal to x squared, and we're trying to differentiate this. So dy by dx, or you can write it as f prime of x as well, is equal to the limit as h tends to 0 of f of x plus h. So you just have to put x plus h into that function, minus f of x, so it's minus x squared over h. We're now going to try and expand it a bit. So we'll have x squared plus 2xh plus h squared minus x squared over h. Cancelling out a bit further, we'll get 2xh plus h squared over h. Cancelling out some h's, we get limits as h tends to 0 of 2x plus h. And you just have to imagine what happens when h is 0. Well, this term will cancel out, leaving us with just 2x. So this will be the derivative of the function x squared. So that's how we prove how we use differentiation from first principle to show how to differentiate certain functions. Let's try another one. So let's try maybe, we're trying to differentiate f of x is x cubed. Same thing. So f prime of x, the derivative, is equal to the limit as h tends to 0 of f of x plus h, so it's x plus h cubed, minus f of x, which is x cubed, like this, all over h. We now have to expand the brackets, so we'll get x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed over h. We can now cancel out a bit, so we'll have limits as h tends to 0 of x cubed over h plus 3x squared plus 3x. Also, x cubed will cancel out, so 3xh plus h squared, like this. You have to imagine what happens when h is 0. Well, these two terms have h terms in it, right? So if h is 0, they will cancel out, leaving us with just 3x squared. So the derivative of x cubed is just 3x squared. Okay, so this is differentiation from first principle. You'll look at using this in pure book 2, where we look at more difficult functions to differentiate.